Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at a very simple proposition which is about the fact that compositions respect continuity. Before that, let us look at what we've done so far. In the previous lecture, what we did was we picked two functions f and g defined on a common domain and assumed that they are continuous at a given point. Then we showed that their sums, their products are also continuous at the same point. And further, if we have this additional condition that if g does not vanish anywhere in its domain, then of course this ratio is then well defined, and further this function is also continuous at the chosen point. As a consequence, we saw that polynomial functions are continuous. Alright, so let us quickly get on with today's lecture. These are the problems. And here is the proposition. So what we have is we have two functions f and g defined on different subsets now, but with the property that the image of f is contained in T, so that if we pick a point in S, we always map inside T. So now we can further apply g to that point. So basically this condition ensures that g composite f makes sense. This is a bona fide function. Alright, so now we fix a point in the domain of f, and this point is such that f is continuous at that point and g is continuous at the image of that point under f. Right? So then the claim is that the composite is also continuous at x0. Let me draw a schematic diagram. This let this denote s and this denote t. And what is f doing? F is taking everything in S inside T. That is what this condition is saying. And this is G, which is mapping to the real numbers. Even though I have drawn blobs, these blobs are really subsets of real numbers. And we have a point x0 where f is continuous. This is fx0, which is where G is continuous. And the claim is that this composite is continuous at x0. And the proof is very simple using the convergence criterion. So what we do is we fix be a sequence in S. Let me not do this. So be a sequence such that xn is in S for all n, and xn converges to x0. Then we want to show that if we compose f and g, then this converges to g of f of x0. This is what we want to show. This will prove continuity by the convergence criterion. So this is very easy because, but by continuity of f at x0, we have fxn converges to fx0. And now by continuity of g at fx0, we have g of f of xn converges to g of f of x0, which is same as saying that g composed f xn converges to g composed f x0, and that's it. That's the proof. Very simple. But this is useful, so let's see some examples, very simple examples. So here what we have is a function which is continuous. Let's say it is continuous everywhere. One can make analogous statements for functions which are continuous at a given point. So we have a continuous function, then define another function g on the same domain. What it does is it consumes a point x and spits out the absolute value of the value which f takes. So then we want to show that g is also continuous, and this is nothing because we have s and this maps inside R, and then we have the absolute value function, and this is ugly. So we have s, then we have R, and then we have the absolute value function which is also valued in R. So we have this composite, and since if we pick a point x0 in S, since f is continuous at x0, being continuous everywhere, it is in particular continuous at x0, and this is continuous everywhere, the absolute value function is continuous everywhere, therefore this composite is also continuous. And this composite is precisely G. Right, so that's it, that's the proof. And let's just take another example where what we have is, we have some function which is again continuous everywhere, and then we define g as the square of f, meaning if it consumes a point x and spits out the square of the value that f takes at that point, and then we claim that g is also continuous. Of course, this is not anything surprising, but using the composite, using the lemma that we proved earlier, it's just immediate, because again s is mapped to real numbers by f, and then the square function which is continuous everywhere, so this is x going to x square, and this composite is nothing but, this composite is precisely g. So therefore g is also continuous. And of course there is nothing very special about 2 here. You could replace this with any n, and still everything is fine. So that's it. Those are the 2 examples. So this was a very short lecture, but I want to emphasize that we should, when faced with the problem of showing the continuity of a function, we should try to break it down as sums and products and composites of already known to be continuous functions, rather than trying to directly apply the epsilon delta on the given very complicated function. It will make life so much easier in general. Alright, so I guess this was all. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.